Welcome to Lecture 2, Variables, Expressions, and Statements. In our first lecture, we built the philosophical foundation. Today, we get practical. We will learn the basic vocabulary and grammar of Python, the fundamental units that you will combine to create all your programs. We start with the simplest elements, constants. These are fixed, literal values. Their value does not change. You have numeric constants like 123 or 98.6. And you have string constants, which are sequences of characters enclosed in either single or double quotes like hello world. When Python sees these in your code, it understands them as specific, unchanging pieces of data. You can print them directly as shown in the shell examples. However, not every sequence of characters is available for you to use freely. Python has a set of reserved words, also called keywords. These words like if, while, def, and return have special built-in meanings in the language. They form the core commands. Therefore, you cannot use these as names for your own variables. Think of them as the predefined verbs in the language. You can't redefine what run means. The list is on your screen. You don't need to memorize it now, but you must recognize that these are off limits for naming. This brings us to the central concept of this lecture, variables. If constants are fixed values, variables are named containers for values that can change. A variable is a named place in the computer's memory where you can store data. You, the programmer, choose the name. The assignment statement using the equal sign, åka is how you put a value into a variable. For example, x ågerston 12.2 stores the floating point number 12.2 in a memory location labeled x. The key power of a variable is mutability. You can later change its content with a new assignment, like x 100. The old value is overwritten. The variable x is now a label for a new piece of data. Since you get to choose names, Python has some simple but strict rules. A variable name must start with a letter or an underscore /thanf. After that, it can only contain letters, numbers, and underscores. So spam23 and the speed are valid. 23 spam, shark sign, and var.12 are invalid. Also, Python is case sensitive. This means spam, spam, and spam are three completely different variable names. Adhering to these rules is non-negotiable. Breaking them causes a syntax error. Rules tell us what is allowed, but best practice tells us what is wise. You should use mnemonic variable names, names that serve as a memory aid for what the variable represents. Compare these two code snippets. The first uses cryptic names like x1q3z9ocd. What does it store? Who knows? The second uses clear names, hours, rate, pay. Instantly, you understand the program's purpose. It calculates pay from hours and rate. As a beginner, you might think words like hours or pay sound so natural they must be keywords, but they're not. They are your choice. Choose wisely to make your code self-documenting. Variables and constants are combined using operators to form expressions. Expressions are evaluated to produce a value. When you add an assignment or a function call, you create a statement, a complete instruction that Python can execute. Look at this sequence. X bow of 2 is an assignment statement. X bow x plus 2 is an assignment statement with an expression on the right, x plus 2. Print x is a function call statement. Understanding this anatomy, variables, operators, constants, functions, is how you start to read and write code. Let's dissect the assignment statement more carefully. It always works right to left. The expression on the right-hand side of the AF is evaluated first. This expression can be as simple as a constant or as complex as a formula. Once the value of that expression is computed, it is then stored in the memory location named by the variable on the left-hand side. In the first diagram, the expression 0.6 is evaluated. It's just 0.6 and placed into x. Later in the second diagram, a new expression 3.9x, 1x is evaluated. Crucially, this uses the current value of x, which is 0.6, to compute a new result, 0.936. That new result then replaces the old value in x. The left side variable is the target. The right side expression is the source of the new value. To build expressions, we need operators. Since our keyboards lack traditional mathematical symbols, we use computer speak. The plus and minus are familiar, but asterisk, OK, is used for multiplication, and the slash for division. Two critical ones to note. a double asterisk is used for exponentiation, raising to a power, and the percent sign percent is the modulo operator, which gives you the remainder after division. For example, 23% 5 equals 3, because 23 divided by 5 is 4, with a remainder of 3. Let's see these in action with some Python shell examples. X plus 2 is a very common pattern. It takes the current value of x, adds 2, and stores the result back into xx. This is how you update a variable. We see multiplication, division, and the modulo operator. Notice the result of division. 1000 gave us 5.28. In Python 3, the /osh always performs float division, returning a floating point result even if the numbers divide evenly. Also, 3 correctly computes 4 to the power of 3, which is 64. When you combine multiple operators in one expression, Python follows strict operator precedence rules to decide the order of evaluation. Just like in mathematics, multiplication happens before addition. The full hierarchy is: first, parentheses have the highest precedence, they force an order. Then exponentiation, UKRMD. Then multiplication, division, and modulo, %, which have equal precedence and are evaluated from left to right. Finally, addition and subtraction, plus, also evaluated left to right. Let's walk through the example. 1 plus 2. 3, 4, 5. First, exponentiation, 2. 3 is 8. Then, division and multiplication from left to right. 8, 4 is 2.0. Then, 2.0, 5 is 10.0. Finally, addition, 1 plus 10.0 gives 11.0. The printout confirms this. My strong advice is this. Rather than memorizing these rules, use parentheses generously to make your intentions crystal clear. Write 1 plus 2, 3, instead of relying on precedence to know you want the addition first. If an expression gets long, break it into multiple statements with intermediate variables. Your primary goal is to write code that is easy for humans to read and understand. The computer will handle either style. A crucial concept in Python is type. Every value, every constant and variable has a type. Python knows whether something is an integer, int, a floating point number, float, or a string, str. The type dictates what operations are legal. The plus operator plus means numerical addition for numbers, but for strings it means concatenation, gluing them together. This is why hello plus there works, but hello plus 1 causes a type error. Python is telling you it cannot combine these different types with that operator. You can check the type of any value using the built-in type_takosh function. Focusing on numbers, we have two main types. Integers, int_char, are whole numbers, positive, negative, or 0. Floating point numbers, float, have a decimal point and can represent fractions. Notice that 14 is an int, but 14.0 is a float. They are stored differently in memory. The type function will clearly tell you which is which. This distinction becomes important for certain operations and for understanding how results are computed. Python often handles conversions between int and float for you automatically in expressions. This is called implicit conversion. If you add an int to a float, the int is converted to a float first. You can also perform explicit conversion using the int and float functions. For example, float 99 converts the integer 99 to the float 99.0. Now, a very important note about division. In Python 3, the // operator always returns a float, even if the result is a whole number. 2 gives 5.0, not 5. This is a change from older languages and Python 2, and it's designed to reduce errors from unexpected integer truncation. The int and float functions are also how you convert strings that contain numeric characters into actual numbers. This is extremely common when reading data from files or users. You can convert the string 123 to the integer 123. But be warned, if you try to convert a string that doesn't make sense as a number, like hello Bob, Python will raise a value error and your program will crash. We'll learn later how to handle such errors gracefully. Speaking of user data, we get it using the input function. This function prints a prompt, pauses the program, and waits for the user to type something and press enter. It always returns the user's input as a string. In the first example, we store that string directly in NAM. If we want a number, we must convert it. The second example is critical. INP as Sakon input Europe floor stores a string like 0A. USF as Saquint INP plus 1 converts that string to an integer, performs the addition, and stores the result. Forgetting this conversion is one of the most common beginner mistakes.